don't want to forget like I did last time. We talked last time about why we care about inner products in general, and the whole idea behind that is to be.
I don't know about anyone else, but I can't like really hear or understand what you're saying.
Okay.
Yeah, it cut out.
Did it cut out?
Oh.
Can you hear me now? Thinking
You
that's
just
enough.
kind of sound like a robot.
Okay.
It sounds like a robot. It like keeps cutting in and out.
Okay. How about, is it any better now?
Yes.
Yeah. My hotspot has been acting up the last couple of days. I'm trying a different spot for my phone. Is it any better now? Do I sound like a robot now? Can you even hear me?
Yeah, not at the moment. You sound normal.
Okay, cool. All right. Well, let me know if I sound weird again. I mean, weirder than usual. All right. So we talked last time about why we care about inner products in general, and the whole idea is to be able to assign lengths and distances to vectors, and then also be able to assign angles between two vectors. So we talked a little bit about, in the Euclidean sense, what those look like, but let's talk about in general what properties we want our inner products to have in order to form what we refer to as inner product spaces. So we use this notation, and now my pen's not working, because of course it isn't. Hold on, let's see if I can try to get the pen to work again. Sorry, lots of technical issues again. There we go. So one of the first inner product spaces, we use the notation, the bracket notation rather than the dot notation. So anytime you think or you see this bracket notation with two vectors inside of it, think about it as our ordinary dot product notation that we use for vectors in Rn. We just use this notation to try to differentiate between a dot, meaning a scalar multiple, versus a dot product of vectors, or what we refer to now as an inner product of vectors. All right, so the first property we want these things to have is a commutativity property. So if I take a V and do its inner product with W, I get the same thing as if I did the W inner product with V. So that's our first axiom that we have, and we can see that I want to try to parallel this with what we talked about in vectors in Rn to start with, just to show that this really does work. When we did vectors in Rn, and just for simplicity's sake, I'm just going to write vectors in R2. So if you had a x1, y1, and an x, well, I'm going to write it as x1, x2 at this point since that's what I wrote, and a y1, y2, when you do their inner product, when you dot product these two together, you get x1, y1 plus x2, y2. Well, certainly, if I would have done it the other way around, I got the same thing. Doesn't matter which way we do it. So commutativity is one of the properties that we want. One of the things that I should mention here that I didn't emphasize to start with is that when we do the inner product, we're taking two vectors and we're turning it into a scalar. Again, the whole idea behind doing this dot product is to help us get lengths, distances, angles. Those are all numbers. Those are not vector things. So this inner product is a function that takes two vectors and turns it into a real number for our purposes. All right, so the second one is a distributivity axiom that says that basically inner products distribute over vector sums. We've seen that type of property before when we've talked about general vector spaces, that we like scalar multiplication to distribute over vector sums. Same kind of idea here with dot products or inner products. So say I added a third vector in here just to illustrate again this property for vectors in Rn, and specifically for what I'm doing here, vectors in R2, just for simplicity's sake. If I did x1 plus y1, comma, I don't know why I put the extra parentheses in there, and then an x2 plus y2, and took the dot product of that with z1, z2, certainly we do our dot product as x1 plus y1 times z1, and our x2 plus y2 times z2. Pardon me. And now this is all just real number multiplication. So I can distribute. And then, of course, regroup. And then we recognize that these are the individual dot products. One of the reasons why I'm going through this, even with what's more of a simple example, I would say, is that one of the things that you'll need to do is verify whether or not something is a dot product, whether or not something is an inner product, much like what we did with vector space axioms. So we're verifying these axioms, and this would be a verification that our usual dot product in R2 satisfies this second axiom here of this distributivity. I'm not going to go through the details of this third one, but it looks like a normal one that we would have if I have a scalar that's multiplied by the first vector and then do the inner product with the second one. I could just go ahead and pull that vector out in front in that way. And that's not something that's unusual for us to be able to pull scalars out. Notice that this is pulling the scalar out of one component. You can imagine that it should be able to pull out the scalar out of the second component. We'll come back to that property in a minute. But notice that if you pull out a scalar from the first component and the second component, they would get multiplied together out in front in that case, because they come out one at a time. Then the fourth one is actually the one that helps us a lot with the idea of length and distance. And it's the idea that if I take a vector and do the inner product with itself, I have to get something that's non-negative. And the second part says the only way that this can be zero is if the vector itself started out to be zero. This is the idea that helps us with length, because let's look at just specifically another vector, a vector in R2. So if I take x1 and x2 and dot it with itself, take the inner product of it with itself, you get x1 squared plus x2 squared. And certainly, if we're talking about real numbers here for our vector components, that's always greater than or equal to 0. And even more so, the only way that I can add two things together that are non-negative and get 0 is if both of them were 0 to start with. Well, if both of these were 0 to start with, then I must have started with the 0 vector. Okay, so that's what this second property says. And also notice that if you do the square root of this, you get what you usually think of as the length of a vector in R2, right? It's the square root of the sum of the squares of those components. That's just a Pythagorean theorem idea, right? If you've got a point out here, I'll call it x1, x2, this length is just the hypotenuse of that right triangle. Pardon me. So the idea of being able to do a dot product, be able to do an inner product, is tied to length in this fashion. So we're going to come back to that idea shortly about how we actually define length of a vector using the dot product. But before we do that, let me do another example here, pardon me, of inner products. This first example is a pretty straightforward example because you can kind of tell why this is going to work before you do anything else. So if we start with polynomials, which you don't typically think of about assigning a length of a polynomial or distance between polynomials, but that's the idea of this inner product, is abstracting this idea to vectors besides ones that are Rn. You can see why this isn't going to work for an inner product, though, because notice all we're doing here is what with our inner product? We're taking the coefficient on the x squareds and multiplying them together, the coefficients on the x's and multiplying them together, and the coefficients, the constant coefficients, and multiplying those together. That's not any different than if I would have said start with a vector in R3 that looked like A0, B0, C0, and take the dot product with A1, B1, C1. That looks like the, goodness gracious, sorry. That looks like the exact same concept, doesn't it? As doing the dot product in R3. So you could go through the vector axioms just like we would with these particular ones and show that those are all satisfied, much like what would have been in the video that you would have watched for today, or for last time, I think is actually when I told you to watch it. So let's do a more interesting one. Let's go down to the second example here and go through the individual vector axioms and see how they work. So in this one, our vector space is going to be continuous functions on the interval from A to B, and we're going to define our inner product as this integral of multiplying the two functions together over the interval. We're not going to have any issues with this being defined, because if P and Q are continuous functions, then their product is also continuous. And as long as you have a continuous function in here, you have no issues with being able to do the definite integral. So we don't typically worry about such details in linear algebra. We know these things, quote unquote, know these things from our calculus classes we would have taken before. But if you go on to, say, an advanced calculus class, you would worry about such things about, oh, is this integral really defined? Can I really do this? And the answer is yes. And the reason why is because we have continuous functions. And if you have a continuous integrand, there's no issue with being able to do the integral. So if we run through the vector space axioms, the first thing we need to do is show that the inner product that we have defined is commutative. So the definition is that we take the integral of the product. Well, these are real valued functions. They have a domain from A to B, but the answers that come out are just real numbers. So these are real valued functions. So these are just real number outputs in our integrand. So I have no problem flipping them around. And then notice that when they're flipped around, that's exactly how the inner product is defined. The second property says we have a distributivity in that left component, that first component of the inner product. So again, using the definition, I'm just going to put the two functions into the inner product. And again, like I mentioned, these are all real valued functions, so I have absolutely no issues with distributing that R of x over the sum. And now we get to use a little bit of calculus. Integrals break up over sums with no issues. So I get the integral of P of x times R of x in that first term, and I get the integral of Q of x times R of x in that second term. And then again, just going back up to the definition of our inner product in this case, we notice that the first one is the inner product of P and R, and the second one is the inner product of Q and R. Any questions at all over the first two axiom verifications here? Well, I'm going to do the next two, but I want to make sure we're okay with those two. All right, well, let's look at the third one here. So the third one says that if you have a scalar times the first one, an inner product with the second, we should be able to move that scalar out. And again, this is all just going to be from our properties of integrals that we remember from calculus. So that first step there is just how the inner product is defined. Since we have the scalar, we can move the scalar to the front. And now we recognize the integral as the inner product. Notice that, again, much like what we did with vector space axioms, we're just going through and verifying that these things are true or not. I mean, it's also possible that what they purport to you as being an inner product may not be. It may not satisfy one or more of these axioms. Now, sometimes the fourth one can get a little tricky because there's a lot in that fourth one. So the fourth one says, remember again, that we need to show that if we take an inner product of a vector with itself, we have to get greater than or equal to 0 no matter what. So this one sometimes can get a little tricky. Sometimes you have to use a little bit of knowledge from, it's not just a matter of verifying a formula. Notice these first three were just verifying the formula worked, right? We just played around with the symbols, it pushed them around and got what we wanted. This one sometimes requires a little bit more thought and a little bit more explanation. So here's the vector inner product with itself. That is now the integral of the function p of x quantity squared. So this is what I mean by now you have to remember a little bit about calculus and knowledge of your functions. Certainly, we know that the p of x squared is greater than or equal to 0 on the interval from a to b. We know that the integral also must be greater than or equal to 0. And if we think about this from a calculus sense, the reason why is, remember your first interpretation of the definite integral back from calculus was area under a curve, and if the curve is above the x-axis, the area below must be positive. So all we're saying here is that since we have a positive function, the area underneath it must be positive. But again, notice it wasn't just a matter of verifying a formula was working, right? The first three was just a matter of, hey, we're just pushing some symbols around and seeing that the formulas all worked. In this case, we actually had to make an argument to say, oh, I know this function, this p of x squared, is positive, or is non-negative, so then the integral must also be non-negative. We also have to show that when you dot product with itself, if you get 0, the only way you can do that is if you started with the 0 function. So let's go the easy way first. If the function is the 0 function, then certainly if I take the function and dot it with itself, we already said that that was equal to, that's equal to the p of x squared But if p of x is 0, I'm just integrating 0 over the interval from a to b. Well, again, if you think, you could actually just go through and compute it, but if you think about it from an area argument, the 0 function is the x-axis. Well, there's no area between the 0 function and the x-axis, so this has to be 0. So remember, though, this is an if and only if, so all I've done is proved one direction. I've said if the vector was the 0 vector, then the dot product with itself is 0. We need to go the other way. If the dot product with itself is 0, then in this case we would have the integral from a to b of p of x squared is equal to 0. Oops, forgot my dx. And now again, this is requiring us to use knowledge of our function. This is a continuous function, and it's non-negative. So the only way we can get 0 out is if the integrand is 0. So just to write that down, since p of x quantity squared is greater than or equal to 0, and since it's continuous, we must have that function is the 0 function. And that gives us that p of x had to be 0. The idea behind the reason why it's important for the function to be continuous in this case is because if the function bumps up above the x-axis, if it actually becomes positive and not equal to 0, then there has to be a whole interval over which the function is bumped up above the x-axis because it's continuous, right? If you think about drawing its graph, you can't lift your pencil when you draw the graph. So if it bumps up above the x-axis, I actually draw the picture on the screen here. If it comes along here and bumps up above the x-axis, there has to be a whole area where it's bumped up above the x-axis, and so this area is going to be positive. So then the integral couldn't have been 0. That's the idea behind this argument here. But like I said, this fourth part, when you're verifying the fourth axiom, it can be a little bit trickier than verifying the other three, because sometimes you have to make arguments like what I just did here. Questions on that part at all? We'll actually do some honest goodness computations here in a little bit, but I wanted to go through a verifying the axioms here. All right. Well, let's talk about some properties of the inner product, and let's just see if we can prove a couple of these. So we'll start with 3 vectors in inner product space and see if we can verify these different properties that must pop up. So this one first says that if you take the 0 vector and do the inner product with any other vector, you must get the number 0. This is not too huge of a surprise, but let's see why this has to be true. Well, the way we do this is the same way we typically do things when we're trying to verify some property with a 0 vector, is use the fact that when you add the 0 vector to itself, you end up still with a 0 vector. So there's no change in that. And then here on the right-hand side, now I've got a sum in the first component, so I can use that second axiom up there to split it up. So this is the axiom 2 above. And now again, these are just real numbers. Remember that the inner product is a function that spits out a real number. It takes two vectors, spits out a real number. So I can just subtract the real number from both sides, and you get 0 is equal to what we wanted. Nothing fancy vector talk there. That's just real numbers. The second one here, it looks like the second axiom just reversed. So not really a huge surprise of why this one has to be true. We'll go through it real quick, and then I'm not going to bother going through the third one because it's the same type of proof. But the reason why this one works is because we have axiom 2, but we also have axiom 1. The first thing we can do is flip the vectors around. So get v plus w comma u. Then distribute. And that's axiom 2. And then rearrange by axiom 1 again. Any questions about either of those two proofs? Hearing none, I'll go on. You should be able, I'm going to leave these last two for you to practice with. This third one, the C, you should be able to do almost exactly like you did for what we just did here for part B. Just do it with axiom 3 rather than axiom 2 in the middle. And then for D here, just remember that your subtraction means that you're adding the inverse. So, like I said, I'll leave those two for you to practice. They're also, well, I don't know if the proofs are in the book. The theorem certainly is in the book. Yeah, it's part of, this is what we're doing here is theorem 6.1.1 on page 303, just to give you the reference. All right, so let's actually do some computations. I promised to do some computations. Let's do some. Okay, so let's first define distance and length, and then we can talk about actually doing some honest-to-goodness computations here as opposed to a bunch of symbol pushing. Although that is my favorite thing to do, as being an algebraist, I like to push symbols. That's what I do. All right, so the norm of a vector, or the magnitude of a vector, or another word would be the length of the vector. Those all three words as far as inner product space all mean the same thing. Norm, magnitude, length, all of those are the exact same word, essentially. So we denote this with what looks like a double absolute value sign. And the definition is we'll do the square root of the inner product of the vector with itself. And this is why that axiom 4 is important for inner product spaces. I want to be able to do a square root of that inner product with itself. If I'm going to do a square root, I'm going to have to make sure that what's underneath that root is not negative. So that's why we need that fourth axiom in the inner product spaces. That's in order to be able to do length. And now for distance between two vectors, the notation we use for that is a d of the two vectors. Well, if we think about this in picture, if you're familiar with vectors graphically, if you've got a v and you've got a u, you know that if I draw the vector this way, that is the u minus v. And it might, in some sense, it might make sense to talk about the distance between the vectors as being the distance between the endpoints. If I want to do the distance between the endpoints, that's going to be the length of this vector. So that's where the distance definition comes from. It's an extension of that idea, again, from Euclidean space. And we're going to do the magnitude or the norm of the difference between the two things. Okay, so let's do this example where we have a different dot product than what we're used to. So this says that we've got two polynomials, and the way we're going to define their dot product is to plug 0, 1, and 2 into each of them and do the product of the outputs in each of the three cases. So we have P of 0, Q of 0, plus P of 1, Q of 1, plus P of 2, Q of 2. So let's just see how this dot product works. So let's do the first one here where we have 2 plus x squared and 3 plus x squared. So the first thing we're going to do is put 0 into both of them. So we'll get 2 times 3. The second thing we're going to do is put 1 into both of them. When we put 1 into the first one, we get 2 again. When we put 1 into the second one, we get 4. And again, the formula says to multiply those two things together. In the third case, we're going to put 2 into both of them. When I put in 2, I get 0, it looks like, for the first one, and I get 7 in the second one. So this gives me 6 plus 8 is 14. Oops, didn't need to scroll all the way off the screen. Okay, so for the second one,
Dr. Joe, can you explain about those numbers?
how I got the 2, the 3, these numbers? Were you asking about the individual numbers? Is that what you asked?
Yes.
Okay, cool. All right, so notice it just says that the first part just says we're plugging in 0 to each of them, right? So this is my P, and this is my Q. So to get the 2, I just plugged in 0 for x and plugged in 0 for x here. That was where I got the 2 and the 3. In the second one...
Oh, okay.
Is that making sense?
Yeah.
Okay, cool. All right, so for part B then, we want to take the square root of the inner product with itself. And again, according to the formula, we want to plug in 0, 1, and 2. And in this case, we're just going to square it because we are doing the dot product with itself. We're doing the inner product with itself. So we'll have 2 squared plus, when we put in 1 there, we also got a 2. So we get 2 squared. And when we put in 2, we got 0. So this gives me square root of 8, which will be square root of 2, square root of 2. And then for the third one, the distance, of course, this is equal to the magnitude of the difference. When I subtract these two, we have negative 1 plus x minus 2x squared. Because I'm just doing the first one minus the second one. Remember the distance here between p of x and q of x will be defined as the magnitude of their difference. And just like in the previous one, we're going to plug in 0, we're going to plug in 1, we're going to plug in 2, and we'll square each of those. When we plug in 0, we get negative 1, so we'll have negative 1 squared. When we put in 1, we get negative 2, so we'll have negative 2 squared. And when we put in 2, we get, 1 minus 8, so we'll get negative 7 squared. If I did my arithmetic correctly on that one. Again, this one's what you get inside each of these parentheses. This is what you get when you plug in 0. This is what you get when you plug in 1, and this is what you get when you plug in 2. And so this gives me 1 plus 4 plus 49 gives me square root of 54. I did my arithmetic right. If I want to be fancy, I'll simplify my radical. Questions on any of those? All right, I want to play around a little bit with just using the properties to do some of these without actually having a specific dot product given to us, just using some of the properties here. So let's look at this one. This is actually number 16 out of your text on page 305. So they give you the way that the dot product works for 3 vectors and then the magnitudes of 3 of them, and it asks you to find these 4, 5 things. Oops, 6 things. Okay, there's lots of things for us to do. Cool. All right, so let's look at the first one. So to save us a little bit of work here, I want to notice something here. Remember that we have both this vector here, the second vector, will distribute over the first one with respect to the dot product. And then likewise, from that other property that we proved, this vector would distribute over this one in the dot product. So essentially what we get is something that looks like what you do when you FOIL, like you did back in high school algebra 1 when you first started learning how to FOIL. So you get a first idea here. This will be the inner product of u and v. Then you get an outer. You get an inner product of u and w. You get an inner. That'll be an inner product with v with itself. And you get a last inner product of v and w. And again, that's just because you have left and right distributivity of your inner product. So it behaves just like what you would see when you do FOIL, because we can just think about it just FOILing out 2 binomials. It behaves exactly the same way. And now we know all of these pieces. We're given that the dot product or the inner product of u and v is 2. The inner product of u and w is 5. The last one here, inner product of v and w, is -3. We're also given this third one because we're given the magnitude. Remember, the magnitude is the square root of the inner product with itself. So this must be the square of the magnitude. So this must be 4. So we get 7, 11 minus 3 is 8. Any questions on that one? Do you see how it's like FOILing?
Yes.
Yes. Okay. Thank you. It's really hard with not being in a class and not getting feedback, at least from looking at people. So thank you. I appreciate that. All right.
No problem.
Okay. So this one would be a similar fashion here. So we have, and then notice we also have that property where we can pull out scalars. We could pull out a scalar from the first one by axiom 2, by axiom 3. We can pull out a scalar out of the second component by that other property that I skipped over and said leave that for you for practice. But it's the same idea. So this would be, I can pull the 2 out, I can do FOIL, do the 2v times the 3u, and pull out each constant. So you would have a 6 times the inner product with u and v and u. When you do your outers, you would get a 4 and then v and w. When you do your inners, you would get a -3 u with itself. And when you do your lasts, you would get a -2 u with w. And again, notice it behaves just exactly like you would do if you were FOILing out 2 binomials. But again, the reason why that works is because we have axioms 2 and 3 plus the commutativity axiom. That allows us to do left distributivity, right distributivity, as well as pull constants out of the first component and the second component. And then again, we're given all of these. Dot product of v and u is the same thing as the inner product with u and v, so that's a 2. V and w is a -3. U with itself, well, the magnitude of u is 1, so this also is going to be 1, because remember, again, we square the magnitude. And then this last one here is 5, and I'm not going to simplify the arithmetic because I'm lazy. C is similar, so you could do C as well, so I'm not going to go through C. Any questions on B? D is an extension of this idea. It just wants you to use the definition. So this is inner product with itself and take the square root. That's the definition of magnitude. And we just saw that we can, basically FOIL this. So what I have under the radical there is not any different than what we did in the previous two parts of this example. It's just basically FOILing out the u plus v times itself. I will notice that before I do anything else, notice it really does look like FOILing because I can rewrite that middle piece as 2 times the inner product with...
I kind of got the robot voice going again.
Do I? Wonderful. Gotta love the robot voice. Is it any better?
Yeah.
Okay. So notice that here in the middle, this really does look like you're squaring a binomial because these two are the same by the commutativity property. So I really could have written it this way. And then it's a matter of just plugging in the different pieces. I believe this was 1 because it was the magnitude of u is 1, so this would be 1 squared. U with v is 2, and then v with itself was 4 because the magnitude of v was 2, if I remember correctly. So this would give you 3, it looks like, if you simplify. Question on that at all? You would handle the last two parts of this exactly the same way, by the way. You just have to make sure you handle the scalars appropriately. So I'll leave those for you to practice. All right, I did want to do one short proof here with this idea. Is there another proof at the bottom, or is that's the last one? Okay, cool. So let's do this last. I want to do this little proof here of showing that how this works, because there'll be a couple of other things that are problems that you'll look at that have this kind of same idea for doing the proof. So we want to show that this identity holds no matter what inner product space you're in. Now, if you remember trig identities from trig class, typically the idea is to make one side look like the other, and you typically use the more complicated side and simplify it to make it look like the simpler side. Well, I hope we can all agree that that right-hand side of that equation is a heck of a lot more complicated than the left-hand side of that equation. Now, one thing you'll probably notice as you look at some of these problems is a lot of them are stated in terms of the magnitude squared rather than just the magnitude. And that's because the squaring gets rid of your square root that's in the definition of the magnitude. So in this case, we would have 1/4 of u plus v, inner product with itself. And notice no square root because we squared the magnitude. And then minus 1/4 of u minus v inner product with itself. And again, no square root because we squared the magnitude. And then again here, now that we have the distributivity ideas for the inner product, this is like foiling. So I'm going to do this quickly. I'll write it as u inner product with itself plus 2, u inner product with v, and then plus v inner product with itself. We just saw this computation in the previous example. We're going to get the exact same thing in the second one, except that it's going to be a minus in the middle, just like what you would see if you were going to FOIL that out for polynomials, for binomials. And now, just to save a little bit of time, we notice that we've got a 1/4 u inner product with itself. Here you'll get a minus 1/4 u inner product with itself. So those two are going to end up going away. Same thing is going to happen with the v inner product with itself, because you got a 1/4 v inner product with itself and a minus 1/4 v inner product with itself. So those two are going to go away. And then finally, 1/4 times 2 gives you a half in the first one. And then minus 1/4 times the minus 2 will give you plus a half in the second one. And gives you exactly what you're trying to prove. Any questions on that one at all? Okay, so like I said at the beginning here, we won't meet formally like a class on Friday. So, but you can feel free to email me if you want to have a Zoom meeting to talk about anything. That's fine. I'm also going to send out a survey, a short little survey for everybody to see how you think things are going for class so far. We've done this for a few weeks now, so I want to make sure seems like they're going okay for you, or if there's anything else that I can do. And it'll be an anonymous survey, so I'm just going to send it through SurveyMonkey. Like I said, it'll be short, but I would like to get some feedback to make sure that I'm doing what I can do to help you through this weird time of remote learning, because it's all weird and new to me too, and apparently I sound like a robot half the time. So anyway. Any questions at all before we say goodbye?
No.
Nope. We good? All right. Well, I'll talk to you all again on Monday then. Have a good one.
Thank you.
Yep. Bye-bye.
No.
Okay. Is it freaking battery that's dying in this pen?